Okay, so let's talk about the homework. So did I share the screen or did I share? Okay, wait. If I do this, do you still see my screen, or sorry, are you seeing like the whiteboard still, or are you
Yeah,
seeing like?
I can see your screen.
Oh, you can see my screen. Okay, so I just want to make sure I'm showing you the whole screen, not just the whiteboard. Okay, so 5.1. Okay, so we have that. This will be actually easier if I boost my other screen, actually, just so I can look at it while I do it. So hopefully you have the homework that you can see. Um, so so we have down a little bit. So 5.1. Don't want to write in red. Okay, we have y is equal to x beta plus epsilon, just our standard setup. Blah 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 blah. We're assuming epsilon as usual is distributed as normal, sigma squared 0, comma sigma squared I n. And then epsilon nu is distributed as normal 0, 1. And we're also assuming that epsilon is independent of epsilon. Okay. So z in RD is this is a constant vector or a deterministic vector. We know that.
Mhm.
And then we say mu hat z is equal to, I don't like how he wrote it. I'm going to write it as z transpose beta because to me that looks better. But he wrote it as beta hat transpose z. But these are the same thing, trust me. Where beta hat is, he actually wrote a typo here. Beta hat is supposed to be x transpose x inverse x transpose y. I don't know why he did the x instead of the x transpose. So just FYI, there's a typo right
Wait,
here. And
deterministic just means constant?
yes, so when someone says a deterministic
Okay.
vector, that means non-random.
Oh, okay.
Z is non-random. So it's not a constant. Sorry, it's not like a C. Like it's like it's not like 5 or
Yeah,
something, but
got
it's
it.
it's non-random.
Got it.
Okay. So to find the joint distribution of, so let's think about finding the joint distribution of mu hat z and epsilon nu. Okay. So first of all, to do that, we need to find, sorry, let me bring this. To do that, we need to find four things. So that's going to be, we need the expected value of mu hat z. Well, really five things. And then we need the expected value of, so the mean vector is going to be this, epsilon nu. We need that. And then we need the covariance matrix, which is going to consist of this, which is the variance of mu hat z, covariance of mu hat z with epsilon nu, and then same over, this is also the covariance,
Yeah.
blah, blah, blah. And then this is the variance. Okay, so this is all we need to find. So first of all, the expectation of mu hat z is going to be the expected value of z transpose beta hat. And we already know that, so this is going to be z transpose times the expected value of beta hat, right? Because z is just a constant. And then we already know that this is just equal to beta. So this is equal to z transpose beta. So we already know that, right? And then with regards to the expected value of epsilon nu, that's already given to us as 0. Okay. So again, now for this other one, we need to find the variance of mu hat z, which is going to equal the variance of z transpose beta hat, which is going to equal z transpose variance of beta hat z. And then that's going to be, so do you know what the variance of beta hat is? We do know that, right? So I don't know if you remember, but it's going to just be z transpose, the variance of beta hat is sigma squared x transpose x inverse z. So it's just going to be that. So it's this, right? So you can simplify that
Yeah.
probably. Okay.
Yeah.
So then
Very
the
quasi.
covariance. Let's talk about the covariance. So I think that's maybe the hard part. So the covariance of mu hat z and epsilon nu, okay, is going to be Where is it? Better. Here it is.
Wait, so for the last part, you just let it remain that way, like
I mean, yeah, you can write it as like sigma squared z transpose x
Oh,
inverse z, but there's nothing really else to simplify here, right?
yeah. Okay.
That's fine, yeah.
Yeah.
Okay, so the covariance between these is going to equal to the covariance of z transpose beta hat epsilon nu. Okay, which is going to equal the covariance of, so if I replace beta hat with what it is, it's going to be x transpose x inverse x transpose y epsilon nu. And then we can actually replace y with what even y actually is, which is going to be covariance of z transpose x transpose x inverse x transpose, and then y is equal to x beta, right, plus epsilon. And then epsilon nu. So then if I simplify this out, you'll notice that this whole term, so everything from like, this summation here, right? All of this is, these are all constants, right? X,
Yeah.
so beta is a constant. Beta hat is not a constant. Beta is a constant. So I can really just write this as z transpose x transpose x inverse x transpose epsilon with epsilon nu, right? And then this is still all a constant. So we don't even have to really care about it. Sorry, the covariance. So then it kind of can be pulled out. So then we get that this is going to be, I'm just going to write this as C. It's going to be like C and then like a covariance of epsilon with epsilon nu. And we already know that this is equal to 0. So they're uncorrelated. And you kind of can do that without even, do you see how I got that?
So I think there should also be a C like on the second last row, because
So here.
you seem to cancel the z transpose and multiplies x beta.
Yeah, so all this, okay, so z transpose times this whole thing here, right, which you're saying should be there, that's a constant, and adding a constant to a covariance doesn't affect it.
Oh, yeah, it's adding, yeah.
Exactly, yeah. So I'm adding it. Yeah, so we're good, yeah, totally. I get what you're saying. So I could have it there, it just wouldn't matter, right? So I just deleted it, just to make it, so this is technically plus b, but then you just get rid of that because it's a covariance,
Okay.
so shifting it doesn't matter, right? Shifting by a constant doesn't matter, right?
Okay.
Yeah. So does that make sense? Does that answer your question? I think that's really the hard part of this question.
Yeah.
The way that I saw that and already knew what the answer was, because it's a lot easier when you know the answer. So I knew it's going to be 0 because I knew that all the randomness in mu hat z was coming from y, right? So this isn't a proof, but in my mind I was like, okay, all the randomness in mu hat z is coming from y, and all the randomness in y is coming from epsilon, right? So I was like, oh, well, if all the randomness in mu hat z is coming from epsilon, and epsilon is independent of epsilon nu, then I was like, oh, it's probably going to be 0. And so obviously you have to still show it. Like that's not a very good answer, but if you know the answer is going to be 0, it becomes a lot easier, right? And then for B, I won't do it, but it's pretty easy because it's just the subtraction. So it's literally just going to be, so you are, now that you found the distribution of this joint distribution, you can just find, so B, you just find, so if, so we found distribution of, so you just do 1 times -1 times, right? You have z epsilon nu. So I won't be doing that, but obviously you can do that pretty quickly, right?
Yeah.
Okay, cool. So then the next one you wanted to go over was, where did I write this down?
The last part of second question. Part
Okay,
E,
5.2e. 5.2e. Okay.
Yeah.
So that was actually not too difficult. So
maybe I just can't really understand that.
no, that's fair. That's fair. There's a little trick.
So
they said,
I also want to make sure that I got both zeros for C and D, but not too sure. Can
You got
I?
zeros for C and D?
Yeah.
That's not right. Do you want me to talk
Maybe you
about
can.
those?
Yeah.
Okay, so were you able to show A and B? Those are a little more obvious.
Yeah.
Or okay, so let's look at B. So okay, let's look at C. So C is a little tricky actually. But and then D is pretty easy once you know what to do for C. So let's look at C. So for C, you want to find the expected value of sigma hat. Okay, so this is a very common one. This is a very common problem. So we actually want to use the fact that we just showed an A. So we want to use that epsilon hat
Yeah.
n. I don't know why it's okay. This is also n. Is equal to, I guess you just forgot to do the n, is equal to this. Okay. So now, something to note is that we said that xi is distributed as normal 0 sigma, right? So remember that that means that the variance of xi is equal to sigma, okay? And something to note is that the variance of xi is going to be equal to the expected value of xi minus expected value of xi times xi minus expected value of xi transpose. So that's the definition of the variance of in expectations of a vector, right? So usually you see it as xi minus expected value of xi squared, but in this case we do it transposed, right? That's like the equivalent for matrix calculus. But then remember, this is both, these are 0, right? So the expected value of xi is 0, right? So then this is equal to the expected value of xi times xi transpose. Okay, so this is a trick you see a lot, right? When you're doing regular
Oh.
regression, right? Or when you're doing regular variables, right? You've probably seen something where the expected value of x is equal to 0, and they say, okay, well, that means that the variance of x is actually equal to the expected value of x squared, right?
Yeah.
Yeah. So it's
Wait.
like the same
I
idea, right?
think. Okay. Oh yeah. Got it.
Are you sure? I can go over it again if you
Yeah.
want. Okay. So yeah, it's very
Okay.
similar to this property. Like we've probably seen that with standard regression. So in this case, it's this. So then from here, you can say that the expected value hat of n, which is equal to 1 over, sorry, the expected value of this, which is going to be the expected value of 1 over n sum I equals 1 to n xit is actually equal to 1 over n sum from I equals 1 to n expected value of xit. And then we just said the expected value of xit is sigma, right? So this ends up equaling 1 over n times n sigma, which is actually equal to sigma, which is a way to say this is unbiased. Does that make sense? So it's an unbiased estimator.
Oh yes. I guess yes.
It's okay. What are you confused about any of the steps?
Um. So. Oh, you just okay.
So I replaced this with
So
sigma.
yeah. I got it.
Okay.
The key point is that like expectation of x is 0, right?
Yeah. So then
Okay.
expected value of xi transpose is equal to sigma. So that's really where we end up getting. So the expected value of xi times xi transpose is equal to sigma. That's why we can replace this with
Oh,
sigma.
okay.
Because
Oh,
this is the
okay.
variance, right? The variance of xi is equal to sigma. So this showed that sigma, which is equal to the variance of xi, which is equal to the expected value of xi transpose. So that's why we can replace this with sigma.
Yeah. Okay.
Okay. And then D, I won't do D, but it's pretty much the same thing. But you just take, I mean, you can't really simplify it that much. I don't exactly know why this question was in here, but just to know the expected value of the trace is equal to the trace of the expected value. So really just go from there. So yeah. And then for E, we have that, again, E is just a constant. So E is non-random or deterministic. And they're saying that the length is 1, and we're saying that sigma is just equal to the identity matrix. So then they ask you to find the expected value of U transpose sigma U, which obviously you can just pull out these. You get U transpose expected, sorry, this is sigma hat. Expected value of sigma hat U, which is just equal to U transpose sigma U. Okay. And then they just said that sigma is just the identity matrix. This is U transpose U, which is obviously equal to 1. Because remember, if the length of U is equal to 1, that implies that the length of U squared is equal to 1, which means that since the length of U squared is U transpose U, means U transpose U is equal to 1. So if you have if you know what the expected value of sigma hat is, which we now know is sigma, it's pretty easy.
Okay. So for part D, like
Yeah.
we need to find trace of sigma, right?
Yes. So you can't really specify it beyond that, though, really. So you can say it's the sum.
So we just
yeah.
So we just leave it there, or saying that the sum of the elements on the diagonal of
Yeah, you
sigma.
basically just have to write in some way the sum of the elements of the diagonal of sigma, but it's sigma, not sigma hat, right? So it is sigma. It's a little different.
Yeah, but we don't actually know the specific elements
No.
of the. Okay.
No. Yeah, we don't know the elements of sigma, so that's pretty much as far as we can get. Yeah.
Okay.
The other way you could write it is that, remember, sigma is the variance of each of them, but I don't know if that really helps. I don't think that's very. It's not really, because you also don't know the variance, so it doesn't really get
you. Yeah.
Cool. Okay, sorry, I don't know where I wrote down which questions you asked. What was your next question?
The last two.
The
questions.
last two. Okay, awesome. Let's do those. Okay, let's look at 5.6. So 5.6, 5.7. Okay.
Yeah.
So 5.6. So we have standard linear regression model where y is equal to x beta plus epsilon. We have that again, mu hat x is the same. It's either beta hat I'll just write it as beta hat transpose x. That's how he wrote it. And then we're saying that mu of x is equal to beta transpose x. So again, A is just really using a very basic fact. So they're just saying that expected value of mu hat of x, which is equal to the expected value of beta hat transpose of x. Well, again, beta hat transpose, we know, so this is equal to the expected value of beta hat transpose times x, because remember, x is just a constant, right? So here, x is a constant. So I know usually, x is always regarded as a constant. And then we know that beta hat is unbiased. So that's something you should already know. So we already know that expected value of beta hat is equal to beta. So then this is just going to be beta transpose x. So if you're looking for proof of this, this is like in the lectures.
So why is that case? So we just assume that beta hat is unbiased. If the
we're not assuming, we already know that. For standard linear regression, that's just a fact.
Okay.
I don't have the proof in front of me, but I would recommend looking.
I don't need. Yeah.
You don't need it. Okay. So beta hat, I know for a fact is unbiased beta. So that's just, you can use that for standard linear regression, which is what we're doing here, right? Just linear regression.
So it's also unbiased, right?
Yeah. And then B asks you to find the variance of mu hat. So this is actually very similar as well. So it's going to be the variance of, I'm going to again do this as, I'm going to write this as x transpose beta hat, just as a little easier for me to think about. So this is going to be, right, we can just pull out the x, so it's a constant, so it's x transpose, or not, yeah, it's constant, beta hat, and then x, right? That's how we pull out vectors from, or matrices or vectors from a variance to do, you know. And then we already, so variance of beta hat is also something you should already know. So this is in the lecture notes. It's going to be equal x transpose, variance of beta hat is equal to sigma squared x transpose x inverse. So this is a little bit confusing. So let me write these in different colors. So sorry, this x is the full x matrix. So I'll write it in red. just to be clear.
It is uppercase, I think.
Yeah, it's
in the-
uppercase. Yeah, it's hard
yeah.
to tell with X's because they look similar, upper and
Oh,
lowercase.
sure.
But yeah,
Yeah.
the black ones are the lowercase, and the red one would be the uppercase version. So this is just equal to sigma squared x transpose x. Trying to make them extra big. Inverse x. And that's all you need to do. And then for C, so you need to do the one above this, but then they ask you to find basically the confidence interval. And so you have the variance, okay? And so then to find the confidence interval, it's just going to be plus or minus, right? Like 1.9, whatever, the t value for t
So
of n minus, yeah, what's up?
it is x beta transpose x plus and minus, right? Like
Yeah. So and then
Okay.
use like s squared for this instead of sigma squared, obviously. You don't know sigma squared. But just replace sigma squared with s squared to get your 9 times confidence interval. Yeah. It's just like anything we find in 9 times confidence interval, it's just plus or minus the t value and then times the standard error. Okay, so that one's not too bad. Again, really, you need to know like your expected values and your variances of your beta half.
Wait.
Yeah, what's up?
Is it referring to problem 5.3? But I don't see.
Oh, he means problem 5.5.
Oh,
right?
okay.
Yeah, is 5.5 is about working? Yeah. So this homework was previously different, so I think that he just forgot to replace the 5.3 with 5.5.
5.5, right?
Yeah. So
So
5.6c is talking about 5.5.
So we just plug in the real numbers for this one.
Yes. Yeah. So your x value would end up being, so now your x would be 1 because you always in the 1, and then so see x, they give you what x is, right? X is equal to 130. And then you have the large x from the problem as well. You have to construct that.
I also have sigma square, I think.
Yes.
Okay.
Yeah.
So
Okay.
beta transpose x is just the response variable, like the y, right?
It's mu hat. So wait, sorry. Well, no.
So
This is equal to mu. So y is equal to x beta, or sorry. So like, well, this is for a specific value. So like, I don't know how to write that. Like, well, I guess what I should say is like y is equal to x beta plus epsilon, and then you'd say
yeah.
mu is equal to x beta. So this is equal to mu, not so mu of x. It's not equal to y of x.
So
Y of x has the epsilon on
it's
it.
just the average of the y, right?
Yeah, it's the average of the points that would occur at y. That's how you'd say
Or
it.
isn't that x bar? Oh, wait. Oh, got it. X bar
Just
is like unbiased estimator of mu, right?
Yeah, sort of. Yeah.
So just okay.
Okay.
Because
That makes sense.
yeah, there are many variables calculated in the 5.5, so it's just a little bit confused.
Okay, yeah, for 5.5. So it's a basic linear regression. So you can look up the formulas for standard linear regression.
Yeah, I did that. I'm just
okay.
saying that it is confusing because I've calculated many like values, so it's
Yeah, that's fair. Yeah, so all you need is for this for 5.6c is just to do all you have to use is really this, and then do the value, and you also have to calculate mu hat x, which is just going to be plugging in, to find the base, right? So you also need to find mu hat x.
When we use the t critical value in the part C, we just use degree of freedom of n-1, right?
N minus
or 2.
2.
Okay.
Because it's n minus p plus 1.
Okay, so
So P is 1, so it's n minus 2.
if we have beta 2, it is n minus 3, right?
Yeah. So it's n
Okay.
minus the number of beta values you have. So in this case, you have beta naught and beta 1. So it's n minus 2.
Okay.
Okay. Any other questions about that one? 5.6?
No, not really.
Okay.
Yeah.
Yeah, what's up?
So for the variance part,
Mm-hmm.
how can you calculate that from 5.5 from the non-values? Because I already know the variance, sorry, the sigma square, and
Yes.
what about the 2x? Like the two x's are different, right?
So this little x
Yeah.
is equal to 1. They give you what it is. It's equal to 130. That vector right
Oh,
there.
okay.
And the big X is equal to a column of ones. And then they give you the column of years of experience. So this will be like 15.1 through 19.9.
Okay, that's fair.
Yeah.
Yeah, thank you.
Okay. Another one? Okay. So 5.7. Okay. Hopefully I can finish or kind of get through some of it. Okay, so 5.7. So we have a little bit of a different situation here where we're saying that now we have y is equal to x beta star plus zu plus epsilon. Okay. We're saying that x, so then you're saying that x, z, and beta are non-random. So there's all dimensions, but I'm not going to deal with those right now. They're all non-random. And then we say that u epsilon have a joint normal distribution where they both have mean 0. They're uncorrelated and they have this distribution. So they're 0, so they're independent. And then they look like this. Okay. Now, it looks a little complicated, but it's actually a lot easier than you think. So A, they want you to find the mean and covariance of y. Okay. So to do that, we just need to find the expected value of y, okay, which is equal to the expected value of x beta star plus zu plus epsilon. Okay. Well, this is going to be, so remember so remember what, so I should say beta star. So remember x, z, and beta star are random. So those don't really matter. So the expected value of x beta star is just going to be x beta star plus z is also non-random. So it's going to be z, the expected value of u, plus the expected value of epsilon. So then what's the expected value of u?
Zero,
Yeah, so this is 0. And then what's the expected value of epsilon?
also 0.
Yeah, so then we just get this is actually just equal to x beta star. Okay. Now for the covariant, what's up?
Yeah.
Okay.
I said okay.
Okay. So the variance of y is going to be similarly the variance of this. Plus zu plus epsilon. Okay, now again, x beta, this is a non-random. So remember, we can just pull this out. We don't need to include it in the variance because shifting by a constant doesn't affect variance. So this is equal to the variance of zu plus epsilon. Okay. And remember, these are, let's look up here. These are independent. They have a joint normal distribution and they're uncorrelated and their covariance is 0. And when that happens, we know they are independent. That is a theorem. So this is equal to the variance of ZU plus the variance of epsilon. And so I'll let you finish that one, but you know, you can just proceed from there, remembering that this is non-random. Okay. And then they ask for the distribution of y. Obviously, it's going to be, since it's going to be a normal distribution. Okay, for B, so they want you to find the joint distribution of y and epsilon. Okay. Well, I'm going to write this as x beta star, okay, plus, sorry, z u, right, because that's what y is, plus epsilon.
Yeah.
And then this is just epsilon, okay? So now I'm going to write this even actually in an odder way, which is going to be, I'm going to write this as x beta star, okay, and then 0. So this is a non-random vector. Plus, okay, and you'll see what I'm doing in a second.
Yeah.
Z times the identity, 0 times the identity, times u epsilon. Okay, so I'm not going to finish this, but I want you to note that you already know this distribution, right? This was given above. So from here, it's essentially a problem of finding, you know, this is essentially now, you know, mu epsilon, find the distribution of basically A mu epsilon plus B, which is something we've done a lot, right? Do you see what I'm getting at? Or do you think you can finish it from here?
Yeah, I think I got it. But how are we
Okay.
supposed to know that we should divide the thing like that? If
Are you,
we met it in a test or something like that.
I don't know. I took this. I took this from answers. So it would be something where you'd have to, you know, you'd have to
Oh,
sort of come up with it yourself. Um, I guess what I recommend. I know it seems so obvious when someone gives you this, but in general, you know, think of what you know. Oh God, think of what you're given, and try to work problems into that. So, you know, we were given the joint distribution of u and epsilon. And so you can kind of think like, okay, I need to get it into the form of something that has u and epsilon kind of vector somewhere, right? Yeah, sorry. That's the best I could say to know what to do. Kind of one of those
okay.
things where it's like mathematical intuition, like, you know, it's
I
not
think
necessarily.
this homework is pretty hard.
This one's really hard. This problem in particular is really difficult.
Yeah, really hard.
Totally. I mean, this is very Amini though. Like this is how his like I remember I had him for some theory-based classes, and it's always like this. It's very difficult. But you know, just don't stress too much. Like people are probably just you know maybe not even keeping up either. They're just. I think it makes you stronger. Okay. So C. Okay, so they kind of go with other stuff. I don't know why they bring this in. C is actually really easy. C doesn't not involve the new stuff. So C just wants you to find, they say, okay, beta hat, the standard beta hat is this, right?
Yeah.
And then they want you to say, is beta hat unbiased or beta star? So what they want you to do is just find the expected value of beta hat, which is just equal to the expected value of x transpose x inverse, x transpose y, which is just going to be x transpose x inverse, x transpose y, x transpose, and then the expected value of y, because y is the only random thing here. And so then the expected value of y is equal to the expected value of x beta star plus zu plus epsilon.
I think it's just x beta star. We have calculated that in part A.
Oh yes, okay, awesome. So yeah, so you can go from there. I won't. I don't want to give the whole answer, but yes, okay. So then you can go from there. It's pretty easy from there. Okay, D. So the last couple of minutes, I do want to help you out a little bit with D because I don't know. E is really easy. So D, they kind of say these things where, okay, let's say that X is equal to, so let me just be real quick here. So sorry.
So I'm
You
sorry.
have to go.
No.
What's up?
I'm just wondering that so it's like some X transpose X inverse times X transpose times X beta stars. So it isn't unbiased, right?
No, so this is X transpose X inverse, X transpose X beta star.
Yeah.
And then notice how this is identity matrix. So
Oh,
this is equal to beta
okay.
star.
Okay.
Yeah, so
Got
it
it.
is unbiased. Okay. Okay, so they say they specify this is true. Okay, and then they also specify that Z1 is in the image of X orthogonal, which is identical to saying that Z1 is in the kernel of X transpose. Okay, because remember, the kernel of X is the image of X transpose orthogonal. So if it's in the image of X orthogonal, it's actually in the kernel of X transpose, and that will come into handy in a bit. And then they also say that Z2 is equal to X2. And another way of saying, I mean, this is not actually, that's not it. So this implies that Z2 is in the image of X. Okay, so we have those two facts. And then they say, find an expression for the covariance matrix of beta hat. So they say, okay, find the variance of beta hat in this case. Okay. So let's write what beta hat is. So remember that beta hat is equal to X transpose X inverse X transpose Y, okay, which is equal to X transpose X inverse X transpose, and then this is X beta star. So this is not the expectation, this is what it actually is, right? Plus ZU plus epsilon, which is actually going to equal, so if I multiply this out, so notice how this cancels out again. So this is actually beta star, okay, plus X transpose X inverse X transpose ZU plus X transpose X inverse X transpose epsilon. Okay. And we're going to actually rewrite this as, you'll see why. This is going to be one, I'm going to multiply this by n, aka divide by the inverse of 1 over n, and then also put a 1 over n here, and I'll do the same thing over here. And then from here, oh, sorry, we also know that, so sorry, another thing we know, and the reason I did that is that we now know, we also know, this is something that's also given, that 1 over n X transpose X is equal to the identity matrix. So that's why I did that, okay? And then the other thing we want to find is 1 over n X transpose. So he did this as a hint to find 1 over n X transpose Z. So this is going to be 1 over n, okay? X transpose Z1, X transpose Z2. Okay, sorry. So once I show this, then I think you can go from there. But X transpose Z2. So all I did was rewrote Z1 as Z1 and Z2 and then distribute out the X transpose, right? Okay. So now remember, we said that Z1 is in the kernel of X transpose, right? So what does that mean? What is this equal to then? If Z1 is in the kernel of X transpose, what's X transpose times Z1?
0.
Yeah, so this is 0. So it's actually 0, 0, 0. So let me write that. So it's the vector 0. Okay, and then we said, so actually let me bring this 1 over n inside. Okay, now for the second thing, we said that Z2 is equal to X2. Okay, so we end up getting here is we have 1 over n X transpose and then times X2, which is actually the third vector in X. So remember that 1 over n x transpose x is equal to the identity matrix, right?
Mm-hmm.
So then if we just multiply this by the third column in x, so if we do x transpose times the third column in x, we'll get the third column of this matrix, right? Because that's what we're doing. So then 1 over n x transpose z2 is actually equal to this, the third column of 1 over n x transpose x. So then we have, so if you want, you might, maybe write that down, try to think about it. So then now we have what 1 over n x transpose z is, and remember that it's equal to this. And then also remember that 1 over n x transpose x is equal to identity matrix. And then now go from there to try to figure it out. Okay, it should be a lot easier now. And we already know. So sorry, this is not a y here. This is a u. I apologize. So we already know what the variance matrix of u looks like, and we know what the variance matrix of epsilon looks like, or the variance of epsilon is. And then we now can simplify this a lot better, and you'll get a much simpler answer. So use this fact that this, so if you notice it, obviously it's like right here. And then this is all over the place. This is here, and go from there to find the variance. Okay, I'm out of time.
Okay.
Do you have any
So
last
I
questions?
think